Welcome to part 1 of the AlphaZero for Connect 4 series. In this video we will be creating our whole Connect 4 environment so that we can actually play a game of Connect 4 in Python code and all the functions that come along with that will help us evaluate the environment throughout our training of our AI algorithm so that we can call these functions and get all of the information we need about the current state of the game. So first, we have 5 functions we'll build in this video. The first is just initializing that empty board. We'll call this at the beginning of every new Connect 4 game. This will set up our empty 6x7 board to start each game. Next, we will have a second function that will allow either player to place a piece in one of the 7 columns of the Connect 4 board. The third function will be to get all of the valid moves possible for either one of the 2 players. And then lastly, we will have a function that will check if the board is currently full and if a player has currently won the game. So we'll start with this getInitBoard function. So we can start by defining getInitBoard. This won't take in any arguments. It will just simply return. We will use the numpy.zeros function. What this does is you can put in dimensions and it will return a numpy array full of zeros with that specified dimension. So in our case, this is 6x7. A standard Connect 4 board has 6 rows and 7 columns. So we'll return numpy.zeros 6, 7, and we can take a look at what the result of this is. Board equals getInitBoard. I've also written up a couple functions to help us visualize what we're actually creating here, nicer than just looking at a numpy array. So I will post these on a link to the code on GitHub for these if you're interested, but basically this is just going to render the board for us throughout the video. So we'll call game.py here, and not surprisingly we have an empty 6x7 board. So the next function we're going to write is a function that will allow us to place a player 1, or we'll call it player or opponent piece on the board. And this will just be called place piece. So we can define this function. And this function will take in the board itself. So we'll need to know what the current state of the board is. We'll need to know who is placing the piece. And this will be either player 1 or player -1. And we'll need to know what column they are playing in. So we'll call this action. This is the typical terminology used in any sort of reinforcement learning environment. This is the action that the agent is taking in the action space. In our case, this will be a number from 0 to 6, which will represent the 7 columns of the board. So how do we actually place a piece on a numpy array? I'm going to comment this out for now, and we can take a look at how we actually. So let's print this board so that we can see it as a numpy array first. And we can see on the right side here our array full of zeros. So the way a numpy array works is it's indexed along the rows, or the row dimension here first, from 0 to 5, and along the columns dimension from 0 to 6. So if we want to place a piece in the bottom row, for example, say in the middle of the board or in this 3rd indexed column here, we would do that by assigning along the 1st dimension the 5th index, and along the 2nd dimension the 3rd index. We'll assign this to a +1 for player 1. And so what does that do to our board? As you can see now, we've placed a piece on the bottom of the board. And we've done that by indexing 0, 1, 2, 3, 4, 5, 0, 1, 2, 3. So what our function needs to do is it needs to automatically calculate the row index from the current state of the board and the column the player has chosen to play in. So you can imagine that if there is already a piece in the bottom of this column, we don't want the piece to end up at the bottom again. We want it to end up, just above the piece that's already played. So the way we're going to do this is we're actually going to count the white space in the board. So if we wanted to play above this yellow piece here, what we could do is we could count the number of white spaces in this column. In this case it's 5, and then we can subtract 1 from that number to get our 4th index row. So to actually implement that in Python code here, in our placePiece function, we'll take our board. We want all of the row dimension, or the first dimension of the board, and we want the action column. So if this was 3, we're taking basically all of the 3rd column. From here, we want to ask how many of these are equal to 0, and the way we can do that, this here will return a list of true or false values. Wherever they're equal to 0, it will be true. Wherever it's a piece has been played in that space, it will be false. So we can basically just sum up those true values, and we get the number of white spaces in that column. And the way we can use this value, as I mentioned before, we can subtract 1 from it, and this is then we'll call it the row index. So this is our row index calculated from the action that the player has chosen. From here, all we need to do is assign, we need to update the board. So board equals board, we want the row index. We want the row index, and the action is the column index. And actually, we're not going to assign this back to board. We're just going to index that one position of the board, and we're going to assign the player's piece that has chosen to play there. So if player 1 is playing, we'll give that value a +1, and if player -1 is playing, we'll give it a -1. Okay, so then after we have updated that position of the board, we can return our board. So now instead of specifying 5, 3 here, we can simply just get our initial board, so we have an empty board, and we can call placePiece, and we can specify that we want to place the piece on the board for player 1 in column 3. And we will assign our, update our board, and we should see here the same array that we put together before. Okay, and in fact we do. So now what would happen if we placed another piece in that same column? We would hope to see that it would jump up to play on top of our previously played piece. So let's just copy that same exact line once again, and let's place 2 pieces in that same column. And in fact, you see our 2 yellow pieces have been played in column 3. One more test, we can place an opponent piece beside it, and our blue opponent here is placed in column index 2. So moving on to our next function, this one is very simply, we just want to create a function that returns what are the valid columns that a piece can be played in on the board. So what would define an invalid column is if the board is completely full and you cannot play another piece in that column. So in a similar way, we're actually going to count the number of white spaces in any given column, but this time we're actually just going to check if that number of white spaces is equal to 0. If there are no blank spaces in the board, then we can't currently place a piece in that column. So let's define getValidMoves, and we're going to only take in our board this time. And what we want to return here is a list of valid moves where where 0 represents an invalid move and 1 represents a valid move. So it would look something like this. So we would have 1 value for each of our 7 columns. We could say where 0 is invalid, 1 is valid. So to do this, let's start by initializing all of the columns to be 0, all of them to be invalid, and then we'll iterate through each column and check if it is valid, and we'll update that accordingly. So we will start and say valid moves call it a list, and we can multiply this by our number of columns. So when you have a single element list like this, basically it will just return the number. It will just take the 0 and multiply it 7 times. We can show that quick. And you can see we have our list of all invalid actions to start. So then we want to iterate for, we'll say, column in range 7. So this will iterate from 0 to 6 because the range here is, I guess that's not going to work. But this will, as we iterate through range 7, we will get 0, 1, 2, 3, 4, 5, 6. And so here we just want to check in the same way. We'll count the number of white spaces. So we can just copy our code from before. We'll call this column instead of action. And if this is equal to, so this is the number of white spaces. If this is equal to 0, actually, if this is greater than 0, then our move is valid. So let's say if the number of white spaces is greater than 0, then we will update valid moves in the column index to be valid, or 1. So in our current board, generated from this code, we should see a valid move in all 7 columns because the board is not full in any of the 7 columns yet. So if we run this, if we run get valid moves on this board, and we print that out, exit. Run game.py. And we forgot to, let's just print our valid moves for now. We want to return valid moves, by the way, but let's also just print it. And we see our valid moves are valid in every column. So now let's test out the reverse of that, and let's actually just fill up one of these columns with pieces and make sure that it is determining that column to be invalid. So to do that, let's just put a piece, let's put 6 pieces in column 3 to fill up that column, and then let's print out valid moves again. And we can see that now that this column is full, our list is showing that column with index 3 is invalid. Okay, so that's exactly what we wanted for that function. We can move on to our 4th function to check is the board full. And this one is similar, except instead of checking this for a single column, we're going to check if there's white space in the entire board. If the board is full, then the game is over and it's a tie. So this one is a pretty simple function. Simply is board full. We're going to take in the board, and for this we can just return right away. We're going to use the numpy.flatten function. Actually, it's board.flatten. So this will return the entire board as a 1-dimensional array rather than a 2-dimensional 6x7 array like we currently have. We're going to check if this is equal to 0 in the same way. So we're going to say if the sum of the empty spaces, so we're counting the empty spaces, if this equals 0, then the board is full. If this is false, then the board is not full and the game continues on. So to test this one out, we should expect that our board is not currently full. So let's just return board full here, and we can print board full. Comment that out. And we can see false. So I'll quickly try to fill up all of the columns of the board. Maybe we can actually just kind of do a quick workaround here so that we don't have to do it one by one. I believe there's a numpy.ones function similar to numpy.0, so let's try that. I'm not completely sure if this is right, but yes, so numpy.ones returns a 1 for every spot in the dimensions you provide. So we have a board full of 1s here, and our board should be full. We actually need to check after. We need to check if the board is full after we create that full board, and we in fact get true. So the board is currently full. In practice, when we use this function, that would be a function that we use to decide is the game over. And in that case, if it returns true, then the game is over. Okay, so we can delete some of this stuff out. And last function, this will be kind of the largest of the functions that we'll be working on today. This will be deciding if either player has won. So we're going to define this function for one of the two players based on an input parameter here. So let's actually add a player as an argument to the function. And basically we will be checking, has the player won? So if we input player 1 here, we're going to be checking if player 1 has 4 in a row. Similarly, if we input -1, we're going to be checking, has player -1 gotten 4 in a row on the board. So the way we're going to do this is, let's pull up our board again. This. I just want to render the board so we can actually take a look here. So the way we're going to check for a win here is we're going to break this up into 4 different pieces. First, we're going to check for vertical wins, so we're going to iterate through the board vertically and see if the player has 4 in a row. Next, we're going to iterate through the board horizontally and check for any case where the player has 4 in a row. And then we're going to do diagonally from the top left to the bottom right. And lastly, we will do diagonally from the bottom left to the top right. So let's start out with the horizontal, or with the vertical win, actually. I can just leave this open here for reference. So we'll start out with the vertical win. And this function will return true if player has won, else return false. So the way we're going to set up this function is we're going to return false at the end of the function, and we're going to set up win conditions along the way. So if it gets to this last return statement, that means it hasn't hit any of the win conditions. So to start with the vertical win, if we think about this, we need to iterate through the columns of the board. So we'll start by iterating for column in range 7. And then we also need to iterate downwards towards the bottom. So we need to check, for example, in column 1, we're going to iterate downwards, and actually we're going to increase our index downwards towards the bottom of the board. But since we're checking for sequences of pieces that are 4 in a row, we only need to iterate through this first 0th index, the first index, and the second index, because 1, 2, 3, 4 from the second index is the bottom of the board. We don't need to check, any further pieces downward, since we need four total pieces in a row. So we're going to say for column in range 7 and for row in range 3. So we only need to go 0, 1, 2, and then we're done iterating. So for each of these, we're going to check if the board, this is a very manual process. We're basically just going to check, do all of these pieces equal 1, or equal player, I should say. So first, so we want to know, in the first column, does the 0, 1, 2, and 3 pieces all equal the player, the input player. So we're going to start with 0, 0, and then we have row plus 1, so 0, 1, 0, 2, and 0, 3. And in Python, you can actually just chain these equal statements like this. It's quite nice syntax to check if all of these things are equal. So in this case, this means that the player has 1, and we can return true. We don't need an else statement here, so we're just going to keep checking our win conditions. If this is not true, we'll move on and we'll check the next one. Okay, so next, this should cover us for all of the columns, all the vertical wins here. So we just went through each column and then 2 spaces down on each row. So we checked all the vertical wins. And let's actually do a test case here along the way so that we can check to make sure this works. So let's place pieces in the first 4 spaces in the 3rd column. And let's just see, does our function return true? Oh, so we need to also pass the player here, so let's just say player equals 1. And in fact, it does say, it does return true for player 1. Let's make sure it says false for -1. And it does not. That's because we need to add the player here. So not only are these things equal, but they also are equal to the player of interest here. So good thing we checked that, and let's try this one more time. So we have an index out of bounds error. And yes, that is because I am specifying the indices backwards. So the column needs to be in the 2nd index position for each of these boards. So we always index the row first and then the column. Okay, so let's try that one more time. And in fact, we get false. Okay, so that appears to be working. So next we can move on to the horizontal wins. So similarly, we want to iterate through the board, but this time we actually want to do it kind of in the opposite way. So if we render our board here, we actually want to iterate towards the right side now. So we're going to start by going through the rows, and then for each of those rows, we're going to go through towards the right side of the board in that row. So we can do this kind of in the reverse direction and start with a row in range 6. So we can iterate down the board. And then for each of those rows, we can choose our column. And we actually want range 3 this time because we're checking up until this column here so that we go 1, 2, 3, 4 and get to the end of the board. So we're going to go through 0, starting with 0, 1, 2, and 3, and then look towards the end of the board. So if we can copy all of this, I believe. Yes, so, but instead of incrementing the row here, we want to increment the column. Okay, so now we can try to set up a horizontal win and see if this function is working. So we will return true. And to set up a horizontal win, we can play in column 3, 4, 5, and 6, and that should give us a horizontal win along the bottom of the board there. Okay, so this is not a win for player -1, and that is correct. And let's make sure it is a win for player +1. Okay, so we actually want to go up to 4 in this case instead of 3. So we want to get to the third index, but because the range specifies 1 greater than the last element, this is 4 elements, not the 4th index. So let's try that again, and we get true. Okay, so lastly we need to do our diagonal wins. So these are a bit trickier. Let's say diagonal top right to, actually, top left to bottom right, and top bottom left to top right. We want to make sure we bring this down. So lastly, we need to check our diagonal wins. Start with the top left to bottom right win, and let's render our board here again so that we can just see what's going on here. So for this top left to bottom right win, we need to basically check starting from here, this 0, 1, 2 second index row, all the way down to this space and over to the third index column and down to this space. So this is 0, 3, and 2, 0. And we need to check basically incrementing downward towards the bottom right of the board. So the way we can do this is we can specify for row in range 3 and, as I said, for column in range 4. So we want to check those first 4 spaces along the columns here. And then basically we just want to increment both, this time the column and the row, downward. So if we go down on the row side, we're incrementing by 1, and across on the column side, we're also incrementing by 1. So to go down and to the right, we just increment both the row and the column by 1. I'm not sure what that highlighting is. And we can just ask if board so I'm just going to copy this one actually, save some time, and we can just +1, +2, +3. And if that is the case, we can return true. And I think an easier way to check to make sure we got all of the possible positions here, let's actually just place pieces on the board and visualize it. So we can do a similar thing here. Let's do the same iteration. And let's just say equals 1. So we should see basically yellow pieces in all of those spots that we're expecting that would make up a diagonal win in that direction. So let's run this. Yeah, I'm getting a syntax error. I'm not sure why. Oh, I'm missing an in here, so that's what's throwing it off. Okay, and we do see our diagonal from top left to bottom right wins all covered. So we should be good there. And now let's do the bottom left to top right wins. So this is a pretty similar concept, except instead of iterating through the rows from top to bottom, we actually want to do the same, but we want to do it from bottom to top. So the way we can do this in a for loop is we can say for row in range, we're going to say 5 to 2. So we're going to start from index 5, and we're going to go upward towards the second index, and we're going to do this in the reverse direction. So from there, we want to also iterate through the columns, and the columns we're going to iterate in the same direction, right? We want to go still from left to right across the top of the board. So we can, again, in range 4, and we will check a similar if statement here, but instead of incrementing the rows, we actually want to decrement the row every time. So -1, -2, and -3. And we're still incrementing the columns. We're still checking from left to right across the board and making sure that is equal to the player's piece. In this case, we want to return true. So let's just swap this out and see if we covered the right space of the board. And let's and in fact, you can see now we have the bottom left to top right of the board covered. So I think that will wrap up this part of the series, part 1. We now have basically everything we would need to actually play a full game of Connect 4 in a NumPy array. We just need to call all of these functions. We can place pieces. First, start by initializing our board. We can place pieces in any column we like for either player. We can make sure that the move is valid using this getValidMoves function, and we can check both if the board is full, in which case it ends up in a tie, or if either player has won. In the next part of the series, we'll start looking into some of the more fun stuff. I think we'll start getting into at least the theory and probably some of the code of the Monte Carlo tree searching that we're doing. And we'll start learning how that can actually be one of the key components of this AlphaZero algorithm, and how we can simulate games using these functions we just developed, using Monte Carlo tree searching, and actually develop our training data that will be fed into our network throughout these simulations. So thanks for watching, and I'll see you in the next one.